So if I were to ask you to picture your ideal programming environment, how you'd want to write applications, you might imagine your favorite IDE or your favorite programming language, an environment that makes it really easy to do the right thing, and that has some nice ideals around encapsulation and modularity and that sort of thing. You probably wouldn't imagine writing HTML in a text editor. That probably would not be high up on that list. So the web platform is not this ideal platform to write for, but it's actually getting there. It's actually evolving, and it's getting much better. And we've had this evolution of tooling and conventions on the web, and a growth of component models, like through frameworks with React. Module system contracts. We've invented our own module systems on the web. And we've invented AMD, global systems, CommonJS. And all of these things have just arisen organically. The language isn't owned by anyone. And then compilation approaches and static analysis and build tools. So the whole way we write and run and get JavaScript into the browser is entirely something that's evolved organically. It hasn't really been predetermined. But as that has happened, the negative side of that is that there's this whole array of different ways of going about making apps and different conventions. And nothing works with anything else. And you get this kind of development of a lot of different diverging conventions, which makes it very difficult to work with web application development. Someone new to the platform has a lot to catch up on. They have to understand all these different approaches and ways of going about doing things. So if we want to consider the web as a platform and the way it's developing, it's important that we're thinking in terms of a convergence of conventions. That certain conventions are going to be becoming more popular as we've gone through this organic growth where we've explored the areas of, like, for example, with module systems, to actually reaching a point where we can converge and agree on certain standards. And the standards process helps a lot with that. Because we've got the standards body that's able to take things that users are doing in the wild and then standardize them and bring them into the language and make ways that are going to be a common language for people to work with them. So it's through this convergence of conventions that we can make the web platform easier to develop with. In particular, I want to talk about modularity convergence in JavaScript. So this talks really about how we are thinking about converging the ways we deal with modules in the browser. And if every other web language, every other language that you think of that you write applications with has a module system. And this is something that's still very new to JavaScript. It only took us 20 years to think that we should add a module system to the language. And we finally got there. It's something that's in the language now, and it's coming to browsers. So what does that mean for the convergence of modular workflows in the browser? Well, we can only build towards future convergence by understanding future concerns. So if we want to understand how modules are going to work in the browser in future, if we want to write modules in a way that's going to be on a convergence path for writing modules well and not having to change the way we write modules every 6 months when a new post comes out, we should think about how modules are going to work in the future and work towards that convergence path. And that's basically the idea of this talk. And how ES modules load in the browser is one of the important factors in determining how we're going to work with modules. So it's no use to just think of modules as a syntax. We have to also realize that modular workflows are how modules load in the browser itself, and think about how that's going to change over time. So how ES modules load in the browser. And this goes into some of the ideas behind SystemDeus and JSPM that first inspired the projects. And it's a bit of a technical deep dive, so apologies if that's the last thing you want at this time of the day. But I'll try not to make it too boring. So we've got the module syntax in JavaScript. We've got the ability to write modules and use this export keyword. And you can export functions, you can export bindings. And then in order to import them, we've got this coming to the browser. This is how the browser will import modules. You'll be able to put a script type equals module tag into the browser. And that then gives you the ability to use an import keyword. So for example, if the piece of code on the top left, if that's in a file called lib.js, I could import that from a URL, /lib.js, and I get that function binding. It'll go and fetch that module it'll execute it and it'll give me back the binding. If I have a module with two variables Q and R, it'll go and fetch them, and then I can import that binding. I can give it another name in my local scope. So that's kind of it. That's how you work with modules in the browser. The script type equals module tag. It was specified and put into HTML, and I think the development version of Edge already implements it. It'll be coming to browsers possibly towards the end of this year. It should be pretty popular, I think. So that's it. That's how modules can load in the browser. And then you can also do a shorthand form and use a source attribute. So instead of having like a script tag, instead of having the module body all inside the module, you can just put a source attribute on there and load that entire module from a separate file. The way that the browser actually loads the modules is it stores each module as a URL. So it has an internal registry of modules, and the registry stores URLs to module namespaces. So for example, that lib file that exported function, it stores a URL called site.com/lib.js, and then it stores the exported binding associated with that URL. So for every URL that you've loaded as a module, you have a list of export bindings on this namespace object. And what that does is it allows you to load a module, and if that module's loaded again, you don't need to re-execute it, you just use the same binding. So this is the way that the module registry works in the browser. And this is what the module tag brings us, is a registry in the browser keyed by URL to module namespace object. Even though I was only importing Q and R, only importing Q in this example, even though I have Q and R, the module namespace object is still going to contain both Q and R bindings in the module table because it had to execute that whole module. So it brings this registry. And to just give some clarity to all that, I can show you a very quick demo that demonstrates how exactly you can write the script type module tag. So in this example, I'm going to load in Babel, which will run in the browser and give me ES module syntax support. And I'm going to just include a polyfill, which allows me to write this today. If we take out the top two, you can imagine that's what the browser of the future is going to look like, where you can just write the script type equals module tag. So that's it. And for this example, I'm just going to do a simple React component render. So I'm going to import React. I'm going to import it from a local react.js file. I'm going to import React DOM from a local React DOM.js file, and create a component and render it into the page. So it's a standard sort of workflow of importing React and rendering something. And just to show that that actually works, it's like the most boring demo you can watch. But it runs. And if you look at the network tab, so there you go. It's executed. It takes a very long time. And that's because it has to transpile in the browser, and it's actually running the whole of React through an ES module transpiler. But it works, and it gives you the experience as if you're in a browser of the future that does this. If you look at React DOM, you'll see it's also just importing from React, and then exporting from the secret DOM do not use or you'll be fired export. So yeah, that's it. If I wanted to restructure this application and put this component into a separate file, I could have done import component from a local component file, and I can adjust the component code to export itself as a default export, which will make itself available. And with that kind of restructuring, you can now see that it'll load another file, component.js, in the network tab. There it loads component.js, and I need to give it, yeah, it's got everything. And then you get the same render. Did I jump a step there? No, I didn't. That's everything. Okay. So that's how it works. That's how you'll be able to use modules in the browser. But now imagine we want to start taking advantage of this in real apps. We've got the ability for the browser to load modules. Is it something that we can really use in any way in production and get something useful out of it? Let's think about that production performance. And for the best possible performance, let's imagine we want optimum module caching. And the interesting thing about modules is you have this module table in the browser, and you could potentially be caching modules in the browser. And what that means is you don't have to download a full bundle of code every time you reload the browser. You can just download the pieces of code that changed. And that's a big benefit of having a granular cache and a module registry in the browser itself. So let's try and think towards that case. If we want to have the best possible caching performance, the best caching performance is always when there's no request made at all. So if we want to use far future expires, it means using unique URLs. And that's something we do with script tags in the page. That's something we do with CSS. And generally, build tools will hash the output so you can get this far future expires behavior. And the browser doesn't even need to make a request. Now let's imagine, for argument's sake, that we're going to do that with modules by versioning all our URLs. And we could then far future expires all our URLs, and we can get a cached module registry. So we put a version name onto React, and just like I had in that other demo, we've got version names on React itself. And this looks okay, but it breaks down pretty quickly, because if I want to update React, it means changing a version number inside a module import. I actually have to manually go into every module that uses React and change the URL. So there's no central way of managing that. And if I'm versioning my component and versioning React DOM, for the sake of this example, imagine that React is versioned differently to React DOM. I then have to update all the parent modules that are importing from that, because otherwise they're not going to refresh in the cache. So I'm going to have to bump all of those parent module version numbers. And so what you end up with is a situation where if you want to take advantage of far future expires, which give the best possible caching in the browser, you're going to have to cache flush everything. Like if you change a child import, you're going to have to clear all the parent modules that import that. And you end up not being able to take advantage of far future expires at all, basically. So it doesn't work, is the short point. What we really want to be doing is writing something like this. If I could write something like this, I wouldn't need to update my reference to React in every single module, just like you do in most modular languages. And that reference can actually be something that the exact URL of where to find React can be something that can be determined at runtime. And the spec actually makes allowance for this. So this is the resolution part of the HTML spec that defines loading of modules, where it passes it as a URL. And in the middle there, you can see how it deals with this case, where if you're importing something that's not a relative URL, it's not any type of URL syntax, it doesn't start with a dot / or / or a dot //, then, and it's not a URL at all, then it's seen as a plain name or a bare name, things like jQuery or web / crypto. And in these cases, the spec will actually throw instead of trying to treat that as a relative URL. So what the spec's done is it's reserved this behavior of plain names in the browser to be able to enable in future the ability for module loaders and browser resolvers to indicate how to resolve these names in the browser. So this is kind of set to be something to be provided in the browser in future, and that's basically dynamic module resolution in the browser. That you can take those plain names in modules and determine how to resolve them in the browser at runtime. So basically the summary of the talk up to this point is, if browser module loading might benefit from dynamic resolution in future, then it's probably something worth researching today in terms of how you approach dealing with modularity in the browser and workflows around modularity in the browser. So let's think about that. How could we make dynamic resolution work in the browser? Well, the simple, naive way to do it would be to have a manifest. So you just have a table that says, if you're loading React, get it from this URL. So we can have some kind of system of just saying, pointing React and React DOM to the URLs that they should be loaded from. And if we go back to our original example, components, we now, in the imports for that component, we don't have to write version URLs or relative URLs, or even have a JS extension for React and React DOM. We can just write these plain names. And now if I want to update React, I can far future expire all of these modules in the registry. If I want to update React, I just update that manifest. So I just bump the version in the manifest, and then the browser will know when it sees React, it has to download 15.1.1 instead of 15.1.0. And that means only one file has changed in the module registry. All the other modules in the registry can be cached in the browser and still present. So if this is your application and these are the modules that are running in your users' browsers, and you update React, you only have to update one module in their entire module cache. All the other modules that they have in their cache can stay the same, and you get an optimum network profile. So dynamic resolution allows for the optimum caching of individual modules in the browser. And the other cool thing it enables is fully modular CDNs. And this is the really exciting idea that kind of got me started on JSPM and SystemDeus, which was this idea that if you take this manifest, you can actually just then point React and React DOM to a CDN. And React DOM imported from React. It has an import, that secret DOM, do not touch or you'll be fired, from React. And if it's just encoded a plain name, the text React, instead of having to try and know where that URL is located, our local manifest can determine the resolution of all the modules. So the CDN doesn't need to know exactly which version of React you're using and where it's located, and you get this ability to have fine-grained caching of modular CDNs. So you could have a public cache, just like you have used jQuery from CDN today, but of much more complex libraries. So libraries that have subdependencies and subdependencies of those dependencies. You could have all this in a public cache, like a public registry that exists in your users' browsers already. And what that means is when someone visits your application or website, shared public code can already be in the user's cache. They can already have React in their cache. They can already have React DOM in their cache. They can have subdependencies, all of those to exact version numbers, far future expired, so their browser doesn't even need to request it. And that removes the need to redistribute the same public code bundled over and over again. You know, today we build these large bundles of 1, 2 megabytes, and you make one version change, you have to rebuild the whole thing. And with this kind of approach, you just have to send the user the modules that you want to send them. So it's a way of structuring the runtime of the application into fine-grained modules. You still choose how you want users to use different versions. So you can select the version of React you want to run, and you can load a component that was written for React that just says import React. And you can select how that should resolve. So you choose your own version lock through this kind of manifest system. So I think it's quite an interesting idea. I think it's quite a compelling idea. But is it something that can really be practical? Is it something that can really be fast in the browser? And if you imagine we had the ability to do this dynamic resolution and you put a script tag into the page, and it loads our app. You're sending a request off to the server to load the main file. Only when you get that request back, do you look at those modules, and does the browser then see, okay, we need to resolve React to this URL, React DOM to this other URL. So you have to gradually discover the dependency tree as the modules are loading. And what you end up with is latency times tree depth is the amount of time, is your upper bounds, the amount of time you can load a module. Which is not good, because if you have a module tree where you had, say, a depth of 10 or 20 modules, and it took 100 milliseconds each time, that's 2 seconds just waiting for the dependency tree itself to be discovered. So this is where HTTP2 push comes in. If the server has a copy of the resolution manifest, it can push those resources to the user already with a cache digest, so it's not going to send unnecessary modules. But the problem with dynamic resolution in the browser is that CDNs don't necessarily have a copy of your exact resolver. If we're dealing with a manifest in the browser itself to do resolution, it won't necessarily know how everything resolves. And CDNs are dumb servers, they're not smart servers. So it makes it difficult. And there's an approach you can use here to basically cache the dependency tree up front as a production optimization of the app, where you basically say for each module in the application, it's going to import these things. And at production time, you can inject a separate manifest to do that. And then you can cut out that latency upper bound, and you can end up with a situation where you can just get it all in one round trip. So that kind of shows that the performance problems are all tackleable, at least in terms of latency and caching. Dependency hinting approaches with dynamic resolution can give the optimum network profile. And in the future, you could imagine that the user's cache of modules could actually be bytecode cached. With developments in WASM, in theory, each module should be cached as bytecode in the user's cache, so that when they're going to your site, they're just having to load the modules that have changed. But today, we don't have the ability to do this. Compilation time in JS is what dominates the execution time of an app, and especially on mobile. Network and latency is generally not even so much of an issue. But practically, and in the future, I think this is something that browsers will start to put more and more pressure on through efforts like Service Worker and WASM, through WebAssembly. So these kind of directions will become something much more possible for optimization in future, and then this kind of granular caching of modules in the browser can actually become a very interesting approach. So to summarize the argument, in theory, dynamic resolution allows for the best performance of JS modules in future. If and when implemented, this significantly alters modular workflows in the browser. And so how can we apply this knowledge today is basically the point. So how can we go about looking at investigating dynamic resolution in the browser today? Well, what is a resolver? The resolver is a function of the module specifier and the parent URL. And it then returns a fully resolved URL. So for example, our specifier could be React or doc/component.js. The parent URL is the fully normalized URL in the registry that's loading it. And this is something that's been talked about a lot at the specification level. The TC39, the committee that designed ECMAScript modules, a team of people from that has actually started working on a loader specification, the WhatWork loader specification, and it contains ideas around dynamic loading in the browser, dynamic resolution in the browser. And this is how it specifies writing a custom resolver hook in the browser. So it's the resolver format just like we saw just now, but through the system.loader, setting a reflect.loader.resolve symbol, and then you can just write a custom resolver like that. So that's how these resolvers are currently set to be implemented. The spec is still somewhat unstable, it may change, but this is where those ideas live today. And this specification itself can be fully polyfilled. You can make it run in browsers. And this is where SystemDeus comes in. SystemDeus takes that loader, that dynamic loader spec, and it builds out a loader that has that same API and allows us to write resolvers like this one. So you can actually start playing around today with this full specification, and it provides a way of writing manifests to do this kind of loading. So I'll just show you what that looks like on our original example to see how we can do that today. So I'm going to start with the same demo render. And instead of having to code in the full URLs to React and React DOM, I can now just write the plain names. So that's the dynamic resolution. And in the main page itself, I include Babel again because I'm transpiling. This is an ES module file, so I need to, if I want to run in the browser, I need to transpile it. I'm including SystemDeus. I'm then configuring SystemDeus. And this here is that manifest. This map configuration is exactly just a manifest to tell the browser where to find React and where to find React DOM and point it to the right URL. I can then import that main file, and it'll know how to resolve everything. So if we run that, loads system, loads main, the React files, and then you get a render. Notice it's still pretty slow. So it's showing dynamic resolution in the browser. It's allowing us to play with dynamic resolution in the browser today based on the future loader spec. And the idea I was talking about modular CDNs, if I want to switch to using React from CDN, I can just do it here. I can just update that manifest. And the same app will now run against Facebook's cache of React and React DOM. And just to show it works, and if you look at the network tab, you'll see it's actually loaded React and React DOM from cache, which means that no request was actually necessary from the browser. But this is still not something I can use in production because I'm transpiling ES modules in the browser. But if I switch this over to, instead of using modular syntax, I can just switch it into CommonJS. Then CommonJS is something we can actually load in the browser without needing to run a full pass through Babel. And I can actually remove that from the page. So we can remove that transpilation part entirely. And we'll get a much faster page load. So now what's happening is I'm just having to execute one CommonJS module on the page. I'm then loading React and React DOM from CDN. And that's actually a production-ready workflow, and theoretically quite good because running React and React DOM from CDN is going to be faster than bundling it up with your own code. So that's the benefit of dynamic resolution from a caching perspective. And then you put this thing out to the world, and you start getting feedback back. So this is a recent tweet, well, not so recent. If my choice is use SystemDeus so I can use AngularJS 2 or not use AngularJS, I will go with not using AngularJS. I hate SystemDeus. This one's slightly more informed, really trying to like SystemJS, but it's just so hard to get normal Node stuff working in plugins, not a fan. So they've understood, that there's this difference. It's a very different way of doing things. And then this one was last night. I enjoyed that. So Angular 2 picked it up. They're really liking it, and it does mean a lot of users, unfortunately. But the point is that it's not enough to just provide a loader with dynamic resolution based on all these ideas and ideals. The JavaScript ecosystem has its own ways of doing things, and the development workflows have to be competitive within the entire JS ecosystem today. It's just not going to work if you have to manually configure this manifest and know exactly how to load everything through SystemJS. And the way it works today is we have this massive ecosystem that's been built up through Node and NPM, which is this ecosystem of packages which work together based on conventions that were determined by Node. The way that you load CommonJS and the way that you write modules in CommonJS and that they resolve. And all our tooling for JavaScript is built around these conventions. So how to support compatibility with these existing ecosystems? And SystemJS can actually load CommonJS as we saw. It can load it fine. But the problem is that it doesn't load it with the same conventions of resolution. And so you don't get the full resolution working out. But you can make it work out with the right configuration. So if you know how to configure SystemJS, you can make it load anything. And this is where JSPM comes in. So it basically acts as a configuration management tool for SystemJS, where it can tell it how to load everything, and then assist with common tasks and workflows. So you can kind of take a lot of the grunt work out of having to think in terms of this loader that's going to have a certain set of rules, and share configurations, and it can automatically generate configurations as well. So let me show you how that looks. So for this example, I'm starting a new project, and it's not an existing JSPM project, so it's going to run through the initialization process. And what I'm going to do is install a package directly from NPM, the Material UI package, which is a React-based Material UI implementation. So I actually have to write install correctly. And then this will take me through the inner prompts, and I can use all the defaults. And the only one I'm going to change is the base URL to be the current folder because I'm running on a file URL scheme, just for the ease of these demos. So that'll go off and it'll install Material UI from NPM. Now JSPM knows nothing about Material UI apart from where to find it on NPM. And then it's generating the right configurations for SystemJS to know how to load it and converting the resolution to be able to know how to understand it. And then one other thing I need for this demo is JSX support. So we just have to add that. And I can install that itself using the Babel plugin. And when that's installed, again, it's installing directly from NPM, all the dependencies, converting them. And once that's installed, I can add a Babel options to support that. think that's right. So the demo file itself is a demo plucked directly from the Material UI website. It's rendering an example card, and this is why we need JSX support. And then it's rendering it into the page. It's loading from Material UI, and it's loading from React and React DOM, which were installed when I installed Material UI. So in the index.js file, I include SystemDeus again, and then I just include the JSPM generated configuration, which informs JSPM how to load SystemDeus. Sorry, SystemDeus how to load Material UI. And that'll then go off and dynamically link that entire NPM ecosystem into the browser. And we're getting this component rendering. This is actually loaded over 700 modules in the page. This is what happens in Node.js when you run these things. I didn't write the code, I just made it work in the browser. You actually, just like Node.js will dynamically link everything in as you write your common.js require, we can now do this in the browser. And when you're running locally, in theory, there's no reason why that shouldn't be a problem running locally, because we have access to the file system. So this is, yeah, that's it. And the way it's known how to load everything is through this dynamic manifest for SystemJS that's been created that contains all of those dependency resolutions. And so for every module that is going to be required in that NPM package, it then tells SystemJS where to find it. We could then switch to CDN and have everything loaded off a cache CDN potentially. So that's the idea. Obviously, that's not ideal for production. We don't really want to be loading 700 modules to get a simple component. So for production, I can do a bundle. And because JSPM knows how all those modules load, it can easily wrap them all up. So it's the same sort of thing you get with Webpack or Browserify. I can just bundle up demo.js, and I'll use an inject flag here, which just tells it to, it puts the bundle into the configuration file itself. So it's going to know to use the bundle without us having to do anything more than that. And now if I open up that index page, you'll see we've got one build file loaded, and then everything's run pre-bundled to a single file. So you get something that is then much more suitable for production and more similar to a static linking workflow. Yeah, so that's it. So the idea with JSPM is we can now bridge to that whole NPM ecosystem and run things in a way that can work through a dynamic loader and start to force an ecosystem that'll work based on conventions of dynamic loading. So we can actually build an ecosystem around this and work towards having packages that are created in a way that works well with loading in the browser. So the goal of SystemJS is to investigate dynamic workflows today to better understand the convergence of modular workflows in future. If successful, provide a bridge to this future, a workflow that we have today that can build into a workflow of the future. And if unsuccessful, to provide a lesson, another data point on the path of JS module system convergence. So thanks for listening. Yeah. And if there are any questions.
A great talk, thank you for that. Actually, I have one question, and I would like to point out, firstly, one thing, that it is possible today to actually have your dependency merge one, like, for example, heavy libraries like Moment.js or Lodash, Lambda, whatever, and React without SystemJS. Yeah. So you can download them from the CDN and still writing your modules in the common.js style and writing your code that consumes those modules like common.js styles. It is possible to achieve using the Webpack and actually HTML Webpack plugin and externals option.
Right.
Webpack will trick the bundle that so actually the bundle can grab the code those modules from the window object. And I would like to ask, do you see any room for cache API in resolving? Because if we are using HTTPS, we can trick the browser and actually implement logic of of dynamic resolving modules with Cache API.
Right. So you mean through service workers?
Yeah.
Okay. All right. So the first part of that, when you're talking about using resources remotely through Webpack, that involves a configuration process.
But it's quite simple. Like defining externals, then the name, the key. But it is an object.
Yeah.
So the key is actually the name of your module, which will be required or import from.
Yeah. So,
and then
basically, the idea is that you should be able to do that in a way that naturally works with the CDN. And the issue with Webpack is you end up with a proliferation of configuration again, and you have to manage that configuration and maintain it as part of your app. So it's about looking at ways that this can be done automatically, be done in the browser, and move away from traditional build tooling. The service worker stuff is very interesting, and service worker cache could do these kind of rewrites at a sort of a regular expression replacement level. And that's certainly an option. But the actual argument, I used the cache argument in this talk because it was slightly easier to use as a strong argument for dynamic resolution. The stronger argument is actually multi-version. Even once you've rewritten the URLs in the cache, if you want to have multi-version supports, the registry needs to have unique URLs. And so you do need to have a unique URL system in the module registry itself. So that's the cache argument. That makes sense.
Thank you.
Sure.
Hi, Guy. Thanks a lot for this. This is
Sure.
really cool. I like future thinking. The question is, when you had the Babel transpiler there in the manifest, can you have that for TypeScript as well? And then the question related to that is, of course, TypeScript can give some compile errors. So how do you see those compile errors? And then back to Babel, how do you see the Babel compile errors?
I can show you the Babel one if you want to see what it looks like. Babel, it has a really nice error output. So if I just unbundle the app. And say, for example, we had a typo here, something that's not going to compile. If I run that in the browser, you get the full Babel error. So it's pointing to the line number, and it's the error you get from Babel. If you want to support TypeScript, there's a plugin for that, actually a third-party plugin developed by Frank Wallace. And that's because there's quite a bit of it's quite an intricate integration. And he's gone and actually done support for loading typings in the browser and getting the full feedback on that. So we've actually got that working. It's still a bit of configuration. I don't actually watch that workflow too well, but it's showing a lot of success. And Anders Halsberg's even played with it as well. So it's quite nice to see. Yeah.
Will you be able to cache things that like get deleted? So if say someone deletes something like, oh, I don't know, left pad, that it doesn't break the internet?
Well, if you linked it to something like a CDN that's not going to allow deletions, then of course, yeah.
Yes, hi, great talk.
Sure.
As a full stack developer, I focused on main languages, but it's fine when we are in a big company. But when we are making startup, we have problem with that because there is only one senior and a few juniors. And I think that in next few years or next 10 years, JavaScript can take over many backend languages, and we can make a full stack in the JavaScript using Node.js, using this what I have sold today. Is it the real path for the JavaScript for the next years?
Well, I mean, we've got a lot of possibilities with Node.js. JSPM will run in Node.js, so it'll support backend development as well. There's limited compatibility for Node binaries still. So a lot of projects, when you npm install them, they'll actually compile Node binaries at the time of npm install, and we don't support that in JSPM because I don't think a package manager should execute the code of the packages at the time of install. I don't know, maybe that is worth doing, but it just feels like too much of an injection vector. But we get a lot of support for npm, and you can write backend apps with this approach as well in JSPM. It works very similarly to normal Node, but with the dynamic system.import loader.
For this to work well, do we need HTTP2?
Yes, completely. And more than HTTP2, optimizations all the way through the browser that just don't exist yet. So browsers aren't optimized to do this kind of execution. I mean, it's interesting just to look at this local loading with the 700 modules and see how much it's improved just over the last couple of years that I've been working on this. That, you know, loading 700 modules used to take a lot longer, and I think it's going to be interesting to see where that goes. But yeah.
Thanks for the useful overview.
Sure.
One impression I got from your talk was that by introducing dynamic loading, you're also introducing a great deal of complexity in a number of places. So my question is, what does it actually buy you, other than the promise that some of the modules are going to be loaded faster from a CDN than from your own web poster?
Yeah, the ultimate argument has to be performance and future performance. But if the future is not a thing, it doesn't promise much. So the way it runs today, it's very difficult to argue that it has any competitive features over different approaches. And also, as I say, it is a complex area, and that's why it's so important to be researching it, because, you know, if we can learn things doing this kind of development, that can influence workflows and try and resolve the sort of goldfish syndrome in JavaScript a bit as well. Sure.
Okay, thank you for all your questions. Our time is over. Thanks for Guy for great presentation.